Please join me in welcoming to the Distinctive Voices podium Dr. Padhraic Smyth.
Thank you for the introduction and the applause. It's a great pleasure to be here. My talk tonight is going to be rather high level, so I know there's at least one statistician in the audience. We're not going to get into too many details because I wasn't sure of the background of the audience. I think it's pretty broad. I think there might be one equation somewhere in one slide, so we'll keep it at a high level, but I'm happy to chat about details later on. Okay, so there's a lot of talk about big data in the media, and before we get started into the content of the talk, I want to talk a little bit about terminology. So there's big data, data science, data mining, predictive analytics, statistics, machine learning. These, from my perspective, are different names for much the same thing. In other words, algorithms, computer algorithms for extracting useful information from data. Maybe the one exception on that list is statistics, which has a broader agenda, things like experimental design and so forth. But all these other techniques generally are, I have a lot of data, I want to get useful information out of this. So that's going to be the topic tonight. It's interesting if we think about the word computer, if we go look it up. The historical meaning of this word is not a machine, it's a person who computes. And so it's interesting, if you go back to the 1700s, mathematicians and statisticians were looking at data, trying to fit models to data. They had equations, they had data, they wanted to figure out what the coefficients were, and they would hire computers, people, to help them do this. There's a history of this. So in some sense, big data is not a new idea at all. It's been going on since at least the 1700s, and statisticians were in on the act right from the word go. One example would be Carl Pearson, an interesting individual like many of these famous scientists. He was one of the founders of statistics, and he had a team of computers, people, in his lab in London in the early 1900s. So the problem with having your computers be people is that it doesn't scale up. There just aren't enough people willing to sit around solving equations as a team, and so as we get more data, we need to think of other things. Fortunately, Moore's law and technology came to the rescue. So this is a graph that many of you will have seen, 1900 to 2000, and the y-axis, since it's a little small here, I'll read it, calculations per second per $1,000. It's on a log scale. So we're going from, one sort of something per $1,000 up to 10 to the 10. So this exponential growth that we're all familiar with, and indeed it's fitting, we're here in the Beckman auditorium. I was wandering through the wonderful exhibits before the talk, and of course Arnold Beckman contributed to this with some devices that helped with in Silicon Valley in the early days. So there was a real sea change, in terms of number crunching, as most of you know, post-World War II, as computers, electronic computers started to be developed, and this then accelerated miniaturization, transistors, and so forth until we got to where we are today. And again, the kind of usual thing, but your cell phone has more computing power in it now than a supercomputer would have had when I was a grad student. So it's really absolutely amazing what's happened. Not just computing. In addition, there are other factors involved. So storage of data has also gotten exponentially cheap. And this is a plot from Ray Kurzweil from the 1950s. So this is linear in time. And this is showing you bits per dollar, what you can buy for a dollar. And again, it's on a log scale. So as most of us, it's nice to talk to this audience because usually I talk to students whose average age is about 20, and I have to explain to them what life was like back in the, I'm sure there's young people here as well, but most of you appreciate this, so that's really nice. So this ability to store data, we have the ability to compute, we have the ability to store data. There's a few other things as well going on. They're all hardware driven. The sensors, satellites and GPS on your phone, these have become cheap and miniaturized and ubiquitous so we can collect and digitize data. Storage we just talked about, what it means is we're all data owners. You and I and the grocery store and the doctor and everybody has data now they want to do something with. The computational power, Moore's law. In parallel, statisticians weren't sitting around doing nothing. They were developing new theories of how to work with large data sets, complex data sets, and computer scientists started to get in on the act. We'll say more about that. My own area, machine learning, which is kind of like in between computer science and statistics. And also, not to be underestimated, the role of the internet, and again, you will appreciate this, I have to explain again to younger students why pre-internet was a very different world. If you had a data set and you wanted to send it to a collaborator on the East Coast, you had to get a floppy disk or a tape and put it in the mail and send it, and there was a lot of waiting around, and it was slow. There was a lot of pencil and paper thinking while you waited for data. It's amazing now you can just go online and download genome data or satellite data. It's just really transformed things completely. So what's happened, why the big interest now in big data? I mean, some of these things have been happening. Well, these things have sort of converged. There's this great convergence of the hardware and the ideas and the thinking. So there's just a tremendous demand for data analysis. Everybody wants data analysts. They want to look at their data. They want to see what they can do with it. And this is across the board: sciences, medicine, engineering, business, et cetera. And in the past, the way this demand would have been met would have been by, well, you go to your local statistician and they help you analyze your data. This doesn't scale. We just don't have enough statisticians. Now, we're trying to help with that. We have a relatively new statistics department at UCI, but it's still not going to scale. We can't create exponentially more statisticians, you know. And even the statisticians themselves need computers. The data now is large enough and complex enough that even if we had a team of statisticians, it still wouldn't be enough. So obviously, we need sort of to go beyond statistics to handle a lot of this data. So this is my picture of sort of the way I view things, the way things are. So statistics is strategically right in the middle. It's still very important, but it's, you know, combined with applied mathematics and computer science ideas. You also have all of the, sometimes I refer to it as plumbing, to get the data, store the data, access the data, a lot of traditional computer science topics. And increasingly, there is a human factor. We're realizing that having black boxes that fit models to data is not enough. Particularly in the sciences, we need to take into account the scientist and them interpreting, visualizing, understanding what the model is doing. You also have policy and privacy issues, which I won't say very much about. I might mention a little bit at the end, but increasingly important. The other factor that sometimes people forget here is the domain knowledge, the actual knowledge about the data. Where did the data come from? And particularly I find younger people, students, I have to reinforce it with them that this is very important. Data does not exist in a vacuum. It came from somewhere. You're measuring something. And it's easy on a computer to kind of forget that. And it can lead to very silly results. We'll see some later on. So you may have the technology, the ideas, the algorithms, the software, but you really also need to collaborate with the person who really understands where the data is coming from. So this is a complex business. It's not easy, but our goal tonight is for me to tell you a little bit about what's going on and different examples. So I'll start off with a number of examples of big data. It's always fun to show examples, and I think the variety of different places where people are using data, some of these you will know, but some hopefully you don't know. All right, so this is a graphic that Intel created a few years ago. The font is a little small, so I'll highlight a few things. Basically around 2011, they said in 1 minute, in terms of the internet generating data, how much stuff gets generated. And it's a lot. It's a heck of a lot. For example, 200 million emails get sent in 1 minute. Now, the vast majority of those are probably spam, but still that is a lot of information. In fact, I thought this number was a little high. I thought, well, if that's then per day, how many people are on the planet? But I double-checked it with a few other sources, and there's a lot of email floating around. Wikipedia articles. So, 6 new Wikipedia articles per second getting published. That's a lot of knowledge being added, publicly available, that potentially computer algorithms could mine for information or students could use. 2+ million search queries. We'll see some examples of those in a few minutes. Again, there's a lot of interesting information you can glean from search queries that you might not initially think about. So let's look at one of the companies, the well-known company, Facebook, that is collecting a lot of this data in the news quite a lot. And this is already out of date. They don't publish a lot of numbers or graphs about their data, but this came from a talk by Lars Backstrom, a computer scientist who joined them, and he gave a talk, and these are some of his graphs. So they claimed back in 2012 that they had about 500 million users. They're now over 1 billion, and they're closing in on whatever 7-8 billion of us on the planet. Of course, not everybody here is a real person. This is our family dog, Ringo. Ringo gets a mention in the talk. And so, their number of 1 billion is probably exaggerated, but let's say there's 500 million actual people using Facebook. So it's interesting to think about what data gets generated from that. With Facebook, of course, the social network is really the key part, who you're connected to. So on average, each person is connected to 130 users. Now, my guess is that's pretty bimodal. Teenagers, 2,000 close friends, and the rest of us, 10 close friends. But 130 on average. This gives you a graph. This is what I'm calling a graph or a network of 60 billion edges. And just doing computation on this graph, and they've given talks, and I've talked to some of these people, just even storing it or accessing it or searching it is really a challenge. It's enormous. It's bigger than anything we've thought about before. And social scientists are also getting interested in these graphs, trying to understand, okay, this is, typically in social science, if you look at social networks, you might have 100 people in a high school, and you go around and you survey them, and you ask them who their friends are, and it's very tedious and labor intensive, and then you write papers about that, and it's your valuable data set. That's the historical way to do quantitative social network analysis. Imagine having access to this kind of data. It's just mind-blowing. And so it was one of the reasons academics a fair number of them are going to places like Facebook and signing up and increasing their salary, but also getting access to fantastic data sets. As well as the network, other types of data that Facebook is collecting, and this is very valuable to them in many different ways. And Facebook is just one example, as I picked. 30 billion pieces of content, so text content that people are generating and sharing. So you can imagine learning about what are people writing about, what change in language over time, characterizing different people. Photographs, you don't really think of Facebook primarily for photos, but 3 billion photos uploaded each month. And they recently hired one of my colleagues who's an expert in face detection, and they have, probably one of the best face detection algorithms in the world because they have a huge amount of data to train the algorithms on. So this is just a picture of, as you imagine, over time, they're gathering more and more and more data. This is a little out of date now, but from 1 terabyte a day back in 2008 up to, order of 100 terabytes per day, and that's probably order of magnitude bigger by now. So why, what's driving all this activity, companies like Facebook and Google and so forth? Well, it's all, for the most part at the moment, advertising. And the typical click rate on an ad is maybe 1 in 1,000. But that 1 in 1,000, you multiply that by, a few billion people accessing Facebook and Google, and you get fairly large numbers. And so the dollars that used to be spent on Madison Avenue have shifted to the West Coast and are now being spent in Silicon Valley on my ex-grad students for the most part, and a whole industry has been built up. But it's advertising that is driving a lot of the search engines and Facebooks and so forth. So let me explain just a little bit how this works very high level. When you go to a web page like the New York Times, these blank spots, they're like billboards, except there's nothing on them. So from the New York Times point of view, this is what they're putting up. This is their real estate, if you like. And then they sell these slots to middle parties, and there's middle, lots of intermediate parties. But think of sort of a set of middle guys, advertising companies, that will then sell these spaces to Toyota or Walmart or whoever wants to advertise in the New York Times. Now, what's amazing is that this happens in a fraction of a second. When you go to a website, for the most part, they're dynamically calculating who you are, what time of day it is, where you're logging in from, what space is available, how many ads they want to show. And so it's all happening dynamically. They're going to figure out, of all the ads they could show you, calculate which one you're most likely to click on. There's other constraints. It's a complicated optimization problem, but there's learning algorithms that have figured out from your past behavior which ads you're going to get. And Google has done very well, and the other companies, Bing and Microsoft and so forth, have figured out as well how to do this. But if you do a slightly better job at this than the other guy, you make a lot more money. So here, the ads then that are selected are showed to you, but it's all seamless. You don't know that this is going on. There's an incredible amount of computation going on behind the scenes. And a lot of it is using statistical modeling, machine learning techniques to figure out, to learn who's likely to click on what type of ad. Another type of data here is, this is from Dan Russell at Google, is the search query data at search engines. So this is very valuable data. It's not just a free service that they're giving out. This is all the different ways you could spell Britney Spears. And I actually, when I was writing this slide, I was trying to type Britney, and I didn't get it right. So, but this is the correct one, I assume, and there's 500,000 of these, and then it's listed all the number of times all the different spellings were used. And you might say, how does the computer know that these are all the same Britney Spears? Well, they have a very good feedback signal because the people who typed this maybe retyped it, but they all eventually went to some page that is about Britney Spears. So there's a positive feedback signal here they can use, very, very valuable. How is this data useful? Why would anybody care about this? Well, this gives them a massive spell corrector. So this is when you've noticed in the last year or two, typing into search engines, it's auto-completing our queries, and this is where they're getting that data from. And the point here is that they have way better data than I have in my labs at the university. They're getting it from everybody every second. Remember those 2 million search queries per minute a few minutes ago? That's what they're getting, a vast amount of data. So right now, if you want to build, one of the things that's come out of this is that historically in computer science, people built natural language models of language and grammar and very detailed kinds of models. That has been superseded now by purely data-driven approaches. There's just vast amounts of data of people actually typing stuff and saying stuff. So this can also be used in speech recognition, by the way. You can have a language model. This is only 2 words, but if you imagine people typing longer queries, you get a lot of sequences of words. You learn a lot. There's a lot you can do with it. So just the search data alone is very valuable and used quite a lot. There are other fun things you can do with the search data. You can go to the Google pages yourself and find this tool. This is the query beer. And this is the relative number of queries over time for, let's say the blue one here is beer. So it peaks, not surprisingly, at the end of each year. So Christmas is coming, people want to find beer, I guess, and not sure why you query Google about that, but they do. And so it's interesting what you might do with this type of data. You can also look at it spatially. So if we look at it spatially, the darker red is where there's more queries, relatively more queries about beer. Now they've corrected for population size and things like this, and it makes a lot of sense. These are the highest beer states. I haven't been to all of them, but it's plausible, it seems. This is the lowest beer state, Utah. Very plausible. Okay, so there appears to be some signal here. This is not, now you can get carried away and overfit the data and so forth, but one of the interesting things here is, and there are companies doing this now, is monitoring the search queries. Like imagine you're in the music industry and you're trying to detect what's the buzz, what's the new hip thing, the new band. This would be, there's information in here, very useful information. Or you're a social scientist and you're trying to understand, or a political scientist, understand how people are thinking about the current political situation. There's a treasure trove here. They don't give this data out for good reason. There's a lot of personal information in our search queries. AOL did that 10 or so years ago, and it was a disaster, and that ended it. So if you want to work with this data, you have to go to the companies and work internally on it. Doing something a little bit more realistic with that kind of data, Google had a foundation, I think it's not there anymore, but where they did this thing called Google Flu Trends. I'm sure some of you know about this. The gist of it is that the CDC collects data on the flu, and they collect it from hospital visits and doctors' offices, and there's about a 2-week delay before all of that is collected and made available. So there's about a 2-week latency in estimating is there a flu, how many people actually have the flu. So that's indicated here as the red dots. And this is, in each of these graphs, this is the current time. So CDC is really getting you data 2 weeks earlier. What CDC can give you today is what was going on 2 weeks ago. What Google was able to do from the search queries is estimate and then calibrate it with the CDC data. What's the, how many people have the flu right now today, just from people searching on things like flu medicine and things like that. And they learned this as well. They correlated with the CDC data and learned which queries appeared to go up and down. And they did a really nice job. This was a paper in Nature in 2009, and they were able to get the peak before, the CDC got it, and then the downtrend before CDC got it, and further, they were ahead of 2 weeks ahead. Looked wonderful. But there's also a caveat here. This model was left running for a few years, and some of you may know, this year and last year, it's done quite poorly. It turns out it overfit the data, and this is part of the caveat of big data. You can do some very interesting things, but they had sort of fit to the things that were search queries. There was no theory with any of this. It was just pure correlation. And so not too surprisingly, a few years out, it's not doing as well. So a cautionary note, if you like. In addition to our behavior when we are on the web, all these companies really want to be in our house and with us in our pockets. And they want to be with us from, I was going to say the moment we wake up until we go to sleep, but actually they want to 24/7. They want to be with us. And, I'm a little bit, let's see, this could be a good thing or a bad thing. There are certainly potential benefits to all of us. There are also a lot of potential downsides. Nonetheless, this is happening, and so Apple just this week announced that it's moving into this space. Google bought the intelligent thermostat company Nest a a month or two ago, Apple is announcing it's moving in. So this is kind of where they see themselves going. Your refrigerator, your toaster, your TV, your alarm clock, all, Googleized or Appleized or whatever, talking to each other. And this way they can get a better picture of what you're doing when you're not sitting in front of the computer. That's the goal here. And probably most of us here, we'll probably resist and won't care, but it's the next generation, my two sons, that are going to have to grow up in this world, and the younger folks here, I think that this is going to affect more. But it's very interesting what's going on. There's, the sensor technology, these Fitbits, as I'm sure some of you use, that you can wear, noisy data. It's somewhat primitive, but it's starting to get there where you can start recording your physical activity, your sleep, and get a handle on your health. And I think this is going to be a big area. It's still primitive. The data analysis is very hard. It's very noisy data. But it seems like this is going to be one where there will be a lot of interest. You'll go to your physician, hand him your USB. Actually, who's handing USBs anymore? He just wirelessly looks at your gadget and analyzes what you've been. Instead of explaining what's going on the last 6 months, he will have time series record of it. One person who's done this, was doing this, quite a visionary, is Stephen Wolfram. Some of you may recognize him. He's the inventor of Mathematica, got his PhD in physics at Caltech at age 20, born genius, interesting fellow. Let me explain what this graph is. This is something he published, I guess 2 years ago now. This is time on this axis, and this is the 24-hour day from midnight to midnight going through the day. And each dot here is an email that he sent out. So he wrote some software that captured everything he was doing on his computer, and he was, had enough foresight to start doing this way back before any of us were thinking about this kind of thing. And what's interesting, I'm using this as an example of, you can sort of tell what Stephen's life was like as you go through the years. And, you'll see that he's pretty much, he stays up kind of late. This is basically when he sleeps, So there was, what was going on here? Why did it, in fact, so he was working on a book, and his sleep patterns were almost flipping around completely. He was going to bed at 8 in the morning and getting up at 2 in the afternoon. And this is for him, now he's going to bed at 2 and getting up at 9, so return to normal life. The reason I show this is I think this kind of data our personal data about, my data, Google doesn't have this, I have it, what's changing in our lives, and signals, subtle signals, how fast we're typing, how fast we're moving. I think there's a lot that can be done here. He also recorded incoming emails, outgoing emails. This is aggregating as a function of time a day, and meetings, his physical activity, and so forth. I looked at my own email, so to be fair here, and this is my email in my Gmail since about 2005, and this is just total number of emails, and it's a little worrying that it's going up. And, my wife will probably say, that's not a good thing. We need to get that back down there. But this might be the sort of thing you might show to your doctor when, in a few years when you go, like, yes, my stress levels are up because here's my email count. One good thing is I seem to have better sleeping habits than Stephen Wolfram. I might not be as famous, but, here we go. There are these gaps here, and I'll explain in a minute what those might be. So here's when I started using Gmail. There's a big increase. You can see end-of-year vacation time. So my email usage drops at Christmas and New Year's. That's a good thing. At least there's certain times every year where it drops. And you can see that in the data. Foreign trips show up as everything is shifted in time. So this is not where I'm staying up late at night. When I looked at these dates, these are when I was in Europe and using email at a different time of day. So interesting that you can see that. And you might say, well, who would care about this? Well, the phone companies care, for example. So fraud detection, this is one way to pick up fraud. And they have signatures for our credit cards and so forth, even down to time of day when we use them. And so, this is the kind of thing that I can learn about us. I chaired 2 conferences, and these are 2 of the peaks, so on and so forth. There's interesting personal data, so it's not all the stuff that Google owns. We have our own data. The phone companies are another, set of companies that have a lot of data. They have spatial data about us. If you turn on your GPS, mostly it's turned on for various services. Increasingly, search and information is about physical location and maps and where are you. So this is the density in Southern California of cell phone usage for AT&T customers, which is, from a statistical point of view, would be a biased sample. Here it is in New York. You can start to do different things with this data. One interesting sort of toy example that they did, they looked at Central Park in New York. This is the Landsat image, so you can see where it's it is. And this is the cell phone usage in February, when it's presumably pretty cold, and this is in July. And then they took the difference of these two images, and so you can see essentially where are people more likely to be in July than they are in February. I thought this was a very nice piece of data analysis. And for example, one of the things they described in the paper is there's no gates in Central Park, so New York City facilities has an issue with just estimating how many people are in the parks at any given time. So you could use these kinds of sensors to get an aggregate sense from an urban planning point of view of where are people. And there's a lot of interest in this kind of, for transportation and so forth, understanding how people are using public spaces. I have a student at the moment looking at Twitter data. This is tweets over 6 months with people who have geolocation turned on. And what was interesting when we looked at this data, you can see the roads clearly. So this sort of, lots of people going back and forth to Las Vegas, out to Arizona, various towns and so forth. This is the Cleveland National Forest in here. These dots, by the way, are not people just out randomly boating. This is noise. There's noise in this data, kind of uniform noise. So I just can think of it as speckle noise in this image. But again, it's very interesting what you can think about possibly like changes in this data. Now again, it's quite biased. It's tweeters who have GPS turned on, so you have to be careful about interpreting it. But it's interesting what you can get out of it. Okay, just up the road here. It's not all internet and phone data. CoreLogic is a company just off the 55. If you go up the 55, you pass them. They are an interesting example of sort of aggregators of data. So this is more traditional data. They have a database of, on 99% of US properties, commercial and residential. They combine that then with properties that are up for sale and the information that comes from stuff that's being sold at any given time. Tax histories that are public, they can access that. There's a lot of interesting sort of computer problems in terms of integrating this different information because the addresses may be slightly different, the names and so forth. There's a lot of matching and stuff that goes on there. Mortgage applications, loan data, and bankruptcies. So their job, essentially this company is just there to sort of fuse different data sets, and then they sell this in different ways to customers. They do different types of forecasts of housing sales and things like that. But I just put it up there as an example of another sort of big data activity that's going on behind it. Maybe not so much behind the scenes, but it's interesting that it's happening. Sports is being revolutionized completely. So, we had Moneyball, et cetera, but now the real-time stuff has been taking off in pretty much every sport you can think of. So two examples here are soccer and basketball. Video technology is at the stage now where you can track the players and their numbers and the ball. And you can also embed little sensors in soccer boots and things like that. So you can get this real-time time series of who was where the ball was. In fact, the sensors are way ahead of the analysis. If somebody wants to start a company doing analysis of sports data, I think there's a ton of stuff left to be done there. The techniques that are being used at the moment are fairly primitive spreadsheets, histograms, plots, and so forth. But again, it's changing sports quite a bit so that all the teams headed to the World Cup, for example, all have now data analysts going with them. It's really cool time to be a statistician. Hal Varian at Google, chief economist, said a few years ago, it is the sexy job these days. And in some ways, he was right. Politics, as we know from the last election, Raed Ghani at CMU, a colleague of mine, a fellow researcher, got involved with the Obama team, and they really were able to crunch the data and understand it better than the other guys. And next time, it's kind of be escalating. They'll all be trying to hire statisticians now for the next election. Google cars, you might not think data plays a big role here. You might think that maybe they can code up so what the Google car is, no steering wheel. It's just driving itself based on a whole bunch of visual and other types of sensors. But they're training these models. The way this thing is working is it's identifying pedestrians and other vehicles. And these things are built on, they're learning from lots of historical data. So there's huge amounts of data being used. It's a very data-driven type solution that they're pursuing here. And it's actually amazing that they've been able to get this far so quickly. And it's going to be interesting to see what happens. Everything I've talked about so far is business, making money, selling you stuff. Science is also benefiting, which is good news. And there's a lot of different examples. So I'm switching a little bit now to particle physics. The particle collider at CERN in Geneva. the amount of data coming off this thing is absolutely phenomenal. 700 megabytes per second. So, a terabyte is 1,000 gigabytes, and a petabyte is 1,000 times that. You're getting 20 petabytes per year. It's huge amounts of data. So the only way you can deal with this is you have to have computers very efficient to search for these very rare signals, Higgs boson type signals. And you're really looking for a needle in a haystack, and this is a picture of Daniel Whiteson in our physics department, who's one of the key guys doing this, developing software, and he works with in our research center at UCI. Really state-of-the-art stuff. And but this is a little different because this is constrained by the theory. They know essentially what the background is, and they're looking for deviations from that. And but using machine learning algorithms as well, it's quite interesting. Another area where we have a lot of data is remote sensing, looking at the planet. That's been going on for maybe 20 or 30 years now. The MODIS satellite is an interesting one. There's actually two different ones, but it goes over the entire planet, 250-meter resolution in 37 different spectral bands every 2 days. It's an amazing data set. This shows the fires from a number of years ago, the smoke going out. These are ice sheets. Most of this data, 99.99% of it, is not looked at by any single person ever. Scientists, the remote sensing scientists, just can't keep up with it. It's mostly just sitting on disks somewhere in NASA's data warehouses. What the scientists do is they focus in on particular aspects of it, but a huge amount of that data is being unused, which is kind of a pity. But it's there. Jim Randerson, a colleague of mine, recently did a very cool study where they linked changes in the sea surface temperature out in the Pacific with the amount of burning that you get in the Amazon. Amazon deforestation is a big issue, and they were able to find a predictive link there, and very, very nice work. Okay, so whole new fields are emerging. This convergence of these technologies, web and text mining, computational advertising, the social sciences, the other sciences, and a lot of these things are being driven by data rather than by theory. So let me jump in a little bit and give you a little bit more sense of what these models are doing, these algorithms are doing. And I'll go through this fairly quickly. So pretend we're a bank and we want to give out loans to customers. So our data lives in two dimensions. We have the age of our customers and we have the monthly income of the customers. I generated this data randomly, and then I realized I had a trust fund baby in my data set, age 0, and income of $3,000. So we'll see what happens. But I tried to make it somewhat realistic, but it's, yeah. So each dot is a person, it's supposed to be a person. This is a toy data set to get some concepts across. And each dot is represented by two numbers. If you give it as a vector or point, two-dimensional space, age and monthly income. Now what I've done here is I've colored the dots into two types. The blue dots are good loans. Let's say we're lending money to these people. And it's our historical database. And I realized that the trust fund baby also got a loan. Didn't pay it back, though, so he's in the red, or she in the red category. So the reds are the people who didn't pay back. The blues, this would be a very bad bank where half of the loans went bad, but again, it's just a toy example. So what you do generally with this would be an example of a classification problem. You'd use the historical data to try to figure out, as a function of age and income, where should you draw the line? Where should your decision boundary be? And so here's an example of where we might draw a boundary. We'd say, well, most of the red points are over here, most of the blue points are over here. This might be a good place. And this line is going to be some linear combination of age and income. But then again, maybe this one is good. So we're probably going to have to search around. And the other thing is we're doing this in two dimensions. We can draw lines and look at them. But in the real data, we're going to have to do this in hundreds or thousands of dimensions. We can't just look at the picture and see where the line is. So a computer is going to have to do this. A little bit of math. This is my only equation, I think. So equation of a line in two dimensions. We have three parameters, the intercept c and the coefficients for x and y. So this will give us a line in two dimensions. So x and y are the age and income values. A, b, and c are the free parameters. And so learning here, or estimation, and this is really classical statistics, but we're going to super it up to large data sets. We're going to maybe minimize the squared error, minimize the classification error for any particular line. So we want to find the ABC values, the decision line, that minimize the number of errors on the data that we actually have, the historical data. And we hope that the future data is going to look like that. Now that's a big hope, and you have to be careful. The way currently that most banks and internet companies deal with it is they keep retraining the model so they hope to keep up with what's going on. It's not necessarily the most elegant way to do things, but it sort of works in practice. Okay, back to our data. Let's say we fit a line. Here's an initial guess. That it's going obviously not very good. It's not separating the blues and the reds very well. We're going to move this around locally, and you'll see why in a minute or two why we're doing this locally. And we end up here. So this looks much better. We went from an initial guess, and somehow that line moved around to get to a place where it's a much better descriptor of the data. So how does this actually work in practice? Well, we obviously use computer algorithms to do this, and we use something called local search quite a lot. Very, very simple idea. You start with an initial random guess for A, B, and C. That might be our initial line there, the one that wasn't very good. Then you locally compute the error. What will happen if I do a small change in the values? I just perturb them. This is done using calculus. So you get to use your calculus, very cool. It's a method called gradient descent. We find the steepest downhill direction. We take a small step in that direction. We can't go very far because that is only good locally. We don't really know what this error function looks like. And then we move to that new position, and then we recompute the gradient. And we keep going. And we keep doing this until we can't reduce the error anymore. If we're at the bottom of our error surface, we can't go anywhere. And this has many different names, but we call it local greedy search. It's not guaranteed to be optimal and might get stuck somewhere, but it's very simple to implement. And that's good, because we need to be able to do this very quickly, and it's very fast, and it often works well enough that it's a good technique. It's not too complicated, and so forth. So there's a lot of other ideas we can build on top of this, but this is a general idea that's used a lot. So our example was in 2 dimensions with a line. What happens if I have 3 variables? So now I have age, income, and maybe the assets. This is on some normalized scale. It's plus and minus. A third dimension. So our points now are a 3-dimensional cloud. These changed to green because I forgot to make them blue. But they're still the good loans and the bad loans, but now living in 2 clouds in 3-dimensional space. So our decision boundary now is going to be a plane separating these. And so we're going to find it. The beauty of this is, well, let me get to the beauty of it in a minute. We often have more than 3 variables. I mean, it's not just 3. We might have thousands. In fact, this is the way people build these types of models. They put in everything that might possibly be predictive and say, let the algorithm figure it out. Obviously, as we go beyond 3 dimensions, we can't look at the data. We can't plot it. The nice thing is, from a mathematical point of view, as many of you will realize, it doesn't matter. We're dealing with this it's an abstract vector of some dimension, and whether it's 2 or 3-dimensional or 1,000-dimensional or 1,000,000-dimensional, we can't even think what that space looks like, but it's still a vector. There's still a notion of planes and clouds and points and so forth. So the same algorithm will work. It's dimension independent, essentially. Now, there's caveats. I mean, it's maybe a lot harder in the higher dimensions, but we can use the same idea to find the decision boundary, or this hyperplane, as it would be called, in d-dimensional space. And this is, of course, where you have to use computers, because you can't look at the data and see what's going on. They excel for these kinds of problems. And the trick as well here is figuring out that a lot of these measurements that we might have, if we have 1,000,000 of them, 1,000,000 different attributes, are irrelevant to the problem, that you throw away. There's only a few maybe that are important. Okay, so one thing you quickly get to is thinking of your data as matrices. And this is very useful for sort of thinking systematically about data, because if I can turn all my different types of data into a matrix, then I can do a lot. I can write algorithms that just have to deal with a matrix. So the columns here will be attributes, like our age and our income, but there might be many of them. And the rows will be objects or individuals, like our loan customers. And each row is a vector of attribute values for a specific object, and each column is going to be the measured values for one of the attributes. So let's just make it more specific with credit scoring. We have, particular loan applicant is a row, particular column is one of the variables, one of the attributes we're measuring, and a particular cell then is that, in this example, the age of some loan applicant. Another thing that we can add here is we can have a special column, if you like, that's the thing we're trying to predict, the target variable. And this, for our example of good loans and bad loans, would be binary. Did they pay back the loan? Did they not pay back the loan? Furthermore, we can sort of extend this matrix idea by saying, well, really, we have old data that we know the outcome of, but where we want to use this is on the new data where we don't know the outcome. So imagine we have, the next month's worth of loan applicants, but we don't know in the future whether they're going to pay back the loan or not. So we'll call this our training data. It's used to train the model. And the future data is the data that we really want to optimize for, but we don't have it yet. So we're going to have to use the training data as a surrogate for what's going to happen in the future. And we want to be able to map from the age and income to the variable, how likely are they to pay back the loan. Furthermore, the training data we might overfit. We might, instead of using lines and hyperplanes, we might build something very complicated. And so we'll use test data. And this is analogous to teaching a student. Instead of having them memorize all the training data, like we did here, we'll give them tests. And so we can do this with our algorithms. We can say, we're going to hold out some of the data. You can fit over here, but then predict over here. And they can fit a simple model or a wavy model or a more complicated model. That's all fine. But it's how they do on the test that will really determine how well they do. So this test is really testing the generalization ability. And again, large data is nice here because we can do a lot of this data-driven type of model selection, taking subsets of data to test models. In the old days, if we only had 100 data points, well, it was hard to leave some of it out for testing because we needed all of it to train the model. Okay, so there's a whole industry around this, a whole set of techniques. Let me just give you some sense of what is involved in building different models of complexity. Let's say we only had one y variable and one x variable. So this might be age, and this is something else we're trying to predict. So here's some training data, small data set, tiny data set. So maybe fitting a line to this, maybe it looks a little too simple. It looks like there might be some systematic error here. So maybe I'll go wild and fit a high order polynomial to this. I can fit it perfectly with order n or n minus 1 or something like that. But this is probably way too complex. It's not justified by the amount of data we have. And so maybe this is about right. And the nice thing is, one of the things you get with computers is you can let the data select what complexity is right. And this is very much the philosophy of this data-driven modeling, that there isn't necessarily a true answer, but there is an answer that predicts well or predicts best on our data. And for many of the applications I've talked about, that's what you're after. Coming back to the matrices, this is very nice because it puts us in a world now of linear algebra. We can represent different data types. It allows us to think in a very abstract and general way. The models can be often quite simple, weighted sums of the variables put together in different fashions. And you might be asking, what about those other things you mentioned earlier, images and documents and speech? Well, one of the tricks that people use, and it works well, is sort of figure out how to get it into a matrix, make it into a fixed length vector and put those vectors, stack them on top and make a matrix out of it, and then we're good to go. And that has worked surprisingly well. And I'll give you an example or two. Let's say we have documents. And these could be different lengths of documents, and I'm trying to predict something about the document. So maybe they're emails, and we want to know is it spam or not spam. So I'm going to turn this into a matrix. I feel like a magician here, just watch the over there and it'll happen. How do we do this? Well, it's kind of very dumb. We take all the possible words that we want to have in our dictionary. So we might leave out words like that and because they're not very informative. We'll keep pretty much every other word. So each column here is a particular word, like cat. And then each row here is a particular document. And so what we'll put in the cells here will be the number of times cat is in the document. And the technical phrase for this representation is bag of words. Very imaginative. So every document now is being represented just by the counts of how often did the word cat, dog, etc. And there might be, we're really now in a high dimensional space because the number of words that we might have in our corpus, our set of documents, might be, the number of unique words might be 100,000, it might be 500,000. There's a long tail, a lot of words that could be used. Okay, so this will be our matrix representation. And you can now apply the various algorithms, that local search, finding boundaries, because we're in it's a vector space, we can do it. This is widely used, and it ignores grammar, it ignores sequence, it ignores structure of the document, but there's enough signal and text, just with which words are in there, that you can do very well on a lot of tasks with this. It's a very good place to start. And people have found if you do go beyond this and put in grammar and sequence, you get a little bit of improvement, but it's often not worth the complexity. So this is used very widely in a lot of stuff out there. Here's an example. I think I'll just keep going in the interest of time. What about images? Just a random image here of some of our heroes. And we're looking for, so let's say we're trying to detect, is there a face or not in the image, like our cameras currently do really well. So these rows now are going to be image windows and a particular window in the image. So we'll move, again, they're very brute force. They move sort of a moving window around the image and pick up the pixels. And then these are just the pixels. So it's lost all the spatial information. It's just put the pixel values, maybe sort of raster scan, top left to bottom right, into a vector. And so we've lost any notion of space here. You could replace the pixels by a little bit more information. Instead of the pixel values, you could do little local filters. But you could easily have 1 million columns, things that you compute maybe in a 50 by 50 window or 100 by 100 window, the pixels, functions of the pixels, and so forth. And this is the way a lot of these face detectors and sort of low-level vision techniques work. And it's quite interesting because in the 1960s, 70s, and 80s, there was a lot of effort in trying to put in physics and scene understanding, AI ideas into computer vision. And this has sort of usurped a lot of that. It's very data-driven. And there's a big debate in the vision community as to whether this is a good thing. These things work very well for detecting things like faces, but in the long run, does a system that understands images really need to have a better representation? That's an interesting discussion. At the moment, the data-driven stuff is winning out because the other stuff is very hard to get it to work, and we're not there yet. Web pages, basically you're represented as a cookie on your computer, so that's the rows. And then what they do is they categorize where you've been before. So instead of looking at the actual URLs of pages, they look at what category of the pages. So if you visit a page on soccer, they'll put a count in there. So now it's the number of times that this cookie, you, has visited this category of web page maybe in the past month. So they have this vector now of maybe 2,000 categories, and all of us are in lots of databases around the US where they think they have an idea of what we're interested in. And then they use that to see, okay, people like you, did they click on this ad or not? And then they'll serve us ads and use machine learning to do that. Oh, one technical thing, you do need to know how to map the web pages to categories, but we solved that problem 2 slides back. We know how to map documents, represent documents. We take the text off a web page and we learn. And they use a lot of human labeling to come up with the labels. But once they've done it once, they're good to go. Science as well. Here is gene expression data. This is one of the first papers came out of Stanford. And this matrix is actually sort of turned on its side. These are different genes here, and this is time. It's gone off the edge here. And so we have measurements of the genes at many different times. And you can see there's a lot of structure. This is called a heat map. And so some of the genes are underexpressed, some are overexpressed at different times. So this is an example of clustering. This tree here represents different groups of genes that appear to be behaving the same way. But the key point I want to make is that it starts out as a matrix. Each row is a vector, so very similar algorithms to what I've been talking about to analyze this kind of data. This is known as clustering. Another one that was mentioned in the intro is recommendation systems, which is a big deal, where Amazon has you buying books, but they really want to sell you vacations and gardening equipment and other things. So they want to do this cross-selling, recommending stuff. So imagine that we have customers and products, and maybe they have rated them. This might be the Netflix data on a scale of 1 to 5, but it's very sparse. There's a lot of missing stuff. We don't know, if I like a particular item or not, because I've never rated it or purchased it. So you can imagine this as sort of filling in the matrix, lots and lots and lots of empty cells. We have some cells. We want to somehow figure out how to fill in the rest of it. It's a very interesting mathematical problem, but you can think of it as actually a statistical problem. And I got involved in this with the Netflix prize, made this type of problem very popular. They offered $1 million to anybody who could beat their system by 10%. It turned out their system wasn't very good, but it still took about 3 years to beat it. So it was a very exciting thing from 2006 to 2009. I'll skip over the technical stuff in the interest of time, but the $1 million was awarded in New York. It was very cool. Ended up being a team, very apropos of Chris Walensky, who's a statistician, Bob Bell, who's a statistician, Yehuda Koren, who's a computer scientist, some engineers, so very much collaboration of people on the computing and statistics side. I think it's a nice sort of story about why that blend works well. I'll tell you a little bit about the data plumbing side of it, the organization of data. So a little short sort of tutorial on computer architecture, about as much as I can remember from my undergrad days. We have our CPU doing the calculations, trying to fit that line to that data, but doing it in a million dimensions maybe. We have the local memory, the RAM, the fast memory, and we have stuff out there on disk. And to access a random byte, ballpark, about 10 to the minus 8 seconds to get a random byte of information from RAM, and about 10 to the minus 3 from disk on average, because it has to go out there and physically move the head of the disk around. So this is the random access time of memory. So you can see there's a 10 to the 5 difference, and just to make it concrete, RAM is like 1 meter away, so the person in the front row. The data on disk is in San Diego. So in RAM, I can go get it, come back, do my computation. The data on disk, I have to go to San Diego and come back. That's the difference. So when your CPU is thrashing around and it's taking forever because it's reading data in from disk, this is why. And this is basic physics. You can have more RAM and so forth, and RAM on the CPU and different things, but you're always going to have some data that isn't right up close. And there's the speed of light and so forth. It's going to work against you. So it's very important then to do the engineering, the data engineering, to kind of behind the scenes to make all this stuff work. And so, Google has these massive data centers where they need massive amounts of computation. But I'll go through a quick example. When you go to a search engine and you type in a query, it's amazing what's happening behind the scenes. So back comes the answer to your queries. And if it's 0.1 of a second or maybe up to 0.3 of a second, you don't notice any delay. You think it's instantaneous. If it gets up to 0.8 or 1 second, you actually start to notice. So that's their limit. The engineers cannot go beyond that. So they're doing all kinds of predictions, optimization, but it has to end up on your screen within 0.8 of a second of you hitting return. There's a lot of studies that have shown this. So they talk about tens of milliseconds in terms of bartering between this team and that team and who can be in the pipeline and what they can do. It's a really, I mean, it's great. All our grad students go off and get jobs and have great fun doing this stuff. Now, you have to be able to do this with millions of users and billions of documents. So scaling, that's why they have, Oregon owned with data centers, because they have to scale this thing up. And there's a lot of systems engineering, a lot of parallelization, a lot of optimization. It's really a skilled thing to be able to do this on a large scale. It's one thing for us to do it in our lab and show it works, but then to get it to work for a real search engine is really quite a thing. All right, I'm going to finish last few minutes with cautionary notes. So far, I could be giving the standard computer science, rah, 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 big data is great, we're going to take over the world. I don't quite think that way, maybe because I have more gray hair than some of my colleagues. Let me just go back in time. Usually when I talk about this paper, Tom Swift and his electric factor analysis machine, nobody has a clue who Tom Swift was. But I suspect here there might actually be people. So Tom Swift was I grew up in Ireland, so I didn't grow up with Tom Swift, but a comic book character who liked to invent things, and stories written about him and so forth. And the point here is that when computers started to be used in the 1960s for data analysis, there was a cautionary note struck because data sets were very small, and people were worried that now the idea here is that an electric factor analysis machine was just going to search through the data and be like Tom Swift and come up with crazy, ridiculous answers. So there was a cautionary note back then, and that I think people listen to. And here's another paper in the social sciences where I'll just take one sentence. The role of theory in research is being dangerously ignored in favor of purely empirical work that proceeds without so much as a hypothesis. So at that time, it was very much hypothesis test rather than looking at the data or just letting computers loose on the data. So let me give you an example here of, let's say we look at death rates in the US for kidney cancer. And this is by county. And if you know the answer to this, don't shout anything out. And we look at this map and say, okay, we're going to do some sort of amateur epidemiology here. And we say, wow, it's kind of interesting that maybe in the Midwest there's something going on, in the Rockies and the Southwest, and we don't see anything happening out in the coast, maybe or in the dense areas here. This is, maybe there's something happening. We could do some data mining, come up with some theory to explain that the reason these people live out, they live out in these places. Okay, what about, let's look at the lowest cancer death rates. Kind of the same places, out in the Rockies, down in the Southeast. Okay, well, we can come up with a more complicated theory that says both the lowest and highest. Okay, the point is that this is an artifact of the data. We're looking at counties, and the explanation is as you go into larger and larger population, larger urban counties, the rate, you have more people to estimate the rate. When you're at the small counties, you have very few people. Here's a county with just a few hundred people, and nobody died of kidney cancer. So they have a 0% chance of kidney cancer just from the raw data. So okay, you wouldn't do this. None of us here would do this, of course. But the idea is that if you're not thinking about your data, you can do very silly things. And especially if we let computers loose at the data, they may not know anything about some of the basics. So this is the kind of example I show my students and say you really have to think about statistically. There's no magic bullet here. You have to be careful about what you're doing. So I'll let you look at this slide for a minute. I kind of like it. We see all these medical studies and this and this and this. And then 5 years later, no, it wasn't that. It was the other thing. You need to stop drinking this. So I think there's overfitting going on in abundance. Here's another fun one. This is real data. I didn't make this up. If you aren't able to take this down, you can go to this website and put in your own variables and search, and it's really fun. This has a correlation of 0.95. Okay. Okay, we'll do a different one. We'll do people who died by becoming tangled in their bed. I mean, this is awful. It's sad, but it is the data, So what can I say? Okay. The reason I'm showing you this is just to show that what can happen if you just search randomly for patterns. So you might say, well, we have lots of data. We don't have to worry about it. We have huge, this is small data. This is only a few years, so it's going to happen. But let's go back to, say, climate data. And I'm doing some work with climate folks for a number of years now. And there is literally billions of measurements coming off satellites. So surely we're in great shape here. And so here's the type of thing we do in our papers. We say, oh, look, in La Nina years, this is the precipitation pattern. This is in Southeastern Asia. This is El Nino years. There's a big difference, and there is. And it's, we can start to maybe predict 6 months in advance and look at changes over time, and this is great. But the question I ask, and it was nice to be giving this talk because it gave me a chance to put this up here, how much data do we really have? Do we have billions, or do we have 4 plus 4 plus about 50 years total? So about 8 out of 50 years to work with. I would say we have about 50 data points here if we're interested in climate rather than billions. Or at least 50 is a lot closer to the sort of real number that we have than billions. So it's just saying that you have to think a little bit. You might have a lot of data, and I think this carries over to health as well. Billions of measurements on fitness gadgets and so forth. But really, each individual maybe is a data point rather than all the different measurements we're getting off them if you want to take in variability across individuals. So, the big data hype, this is where the hype comes in. I think we have just more stuff. If you think about it, maybe we don't have as much as we would like. And there's no way to get around this. We can't go back in time, or we try with tree rings and stuff, but we're stuck with looking at the finite window of data that we have. So data is not a magic bullet. Why has it worked well on some of these problems? Well, that I showed you. Well, these are problems with a lot of cheap data. So unlike, say, a clinical trial, I can just grab lots of images off the internet and train a face detection algorithm. They're problems that are relatively static in the sense that when I use them in the future, it's going to be like tomorrow or next week, and I can retrain them, or face detection is not going to change very much. There's not a lot of variability over time in how faces look, for example. And there's problems where theory is not that important. So if I want to build a face detection algorithm in a camera, sure, I could come up with a theory of the muscular structure of a face and three-dimensional models of scenes, but I don't need to. I can do it just off the pixel information. So I think that's where we need to be cautious. So these are the things that work well. There are a lot of problems that don't fit these criteria. And one of the things I worry about as somebody who's involved with big data is that the big data area is being sold and hyped and marketed as a solution to problems in medical research and climate modeling and physics, where I'm not sure that it may help, but it's not going to be the sort of slam dunk that we've seen in some other problems. So in these problems, we really need to combine theory and data. It's obvious, but not necessarily obvious to everybody. I think obvious to the people who would come to a lecture like this, but there's people who aren't quite aware of this. I think I'll skip ahead. One thing I didn't say, another cautionary note, is privacy. There was just a report released by the White House on privacy, and there's a real tension here between what industry wants and government wants and individuals. And there's quite a variability internationally about, Europe is very strong on privacy laws, the US not so great. I think this is going to become a big, big issue, and technologists tend to underestimate the importance of this. I can talk offline to people about that. Concluding comments. I'm running dangerously close to time here. So a lot of research challenges that in big data to address some of these problems. Fundamental statistics is very interesting now. The data are not from a nice random sample. Search queries, they're not random. They're changing over time. How could you model that? And how can you put more theory? How can you, add some theory into this data-driven modeling stuff? The algorithmic questions, how can you work with very large n if something is scaling as n cubed? How can you update an algorithm? This is a practical thing. Can you build a model and keep it going without having a team of 6 PhDs running around after it? Right now, it's kind of good because they keep hiring all my PhD students and employing me as a consultant, but it's not, sustainable in the long run. The human and sociocultural issues. Education, actually, this is a real big one. I met my good friend Ernie Goodman earlier. We were chatting about this. We really have a shortage of people with skills, with statistical skills and computing skills, who can walk in and do this kind of work. And we're not really addressing that challenge right now. It's going to need some change in thinking. And at UCI, we're starting to think about that. We already have a reputation in machine learning, but the thing I want to emphasize, we're starting a new 3-year initiative in data science. I'm heading it up. Starts July 1, but I'm already working on it. This is going to be statistics and computer science at its core, but very much talking to the rest of campus. There will be we're planning a new data science undergraduate major. So send your children or grandchildren or whoever our direction in a year or two. And there's also an important educational component to explain to people the dangers of just unfettered data mining, but also the potential benefits. All right, to conclude, takeaway messages: data-driven modeling, very successful for certain types of problems. But I think some of these other problems are kind of getting brushed under the rug and are going to be more challenging. You're not going to see big data solving cancer in the next year. It's obvious, but it just needs to be said. Statistical thinking is still key. We haven't bypassed statistics here. It's just we're doing it on a different level, but it's still critically important. The data engineering is important. You need the computer scientists. And common sense. It's not a magic bullet. I see this with students a lot. I have an algorithm. It fits to data. I can, go home and no, you have to look at it. You have to interpret it. You have to be kind of an adversary. Think that what might have gone wrong, especially with large amounts of data. Lots of stuff can go wrong. So coming back to the title of my talk, there's considerable hype, but I think there's also a reason for hope. So thank you.
I think we have time for maybe 2 questions.